stars. An example of that I wanted to show you that I didn't do a really good job of explaining was something from Professor Ron Raines's work on Proline. And the story's kind of complicated because it involves something we haven't talked about yet. But it's interesting enough, and it has to do actually with stuff that we're going to talk about in Chapter 2, that I think it's probably worth talking about. So we'll just talk about regular old Proline. To begin with, Proline is a 5-membered ring amino acid. And here is, I guess I shouldn't have chosen that font. So here is the nitrogen of Proline. Here is the alpha carbon, and then proton is down, and then here is the carbonyl carbon. And we'll just use a squiggly line there. Alpha, carbonyl carbon, nitrogen, and then that nitrogen is itself attached to the next amino acid. And then alpha carbon goes to beta, which goes to gamma, and that gamma can be, we won't worry about it for now. We'll just draw a flat 5-membered ring, even though that's not actually how it is, gamma and delta. And Raines showed that, has shown through research over the past 20 years, that there is one reason. How am I saying this? Sorry, I'm not saying it very well at all. Raines investigated the equilibrium between cis and trans amide bond configurations, conformations, beta, gamma, delta. And we just want to be really clear what we mean by cis and trans amides. So the amide bond has double bond character, and this is the omega dihedral angle that we've talked about before. This one would be phi, and this one would be psi. And an amide bond is trans when these two bonds are on opposite sides versus each other, and here the amide bond is cis. Okay. Okay, and one of the things that Raines discovered is that there is an interaction between this oxygen and the carbonyl carbon. And we'll talk about it later, but it involves a lone pair on the oxygen donating into the pi star of that carbonyl. And that interaction is only available in the trans configuration versus the cis configuration, because of course over here the carbonyl oxygen there is on a different side entirely from the carbonyl carbon there. Squiggly line means this could be in a very large peptide. We're just not drawing what's on the other side there. Okay. And they've done some calculations, and we'll talk about this. This is an example of something that's called an N to pi star interaction. The N is the lone pair on the oxygen. The pi star is the carbon-oxygen pi star of this portion of the molecule. So that's layer one of the story, and as I said, we'll talk about that. In a lot more detail. The interesting thing about Proline is that there's not that much difference in free energy between the trans and the cis conformations. If you look over here, this carbon is on the same side as the delta carbon, whereas here it's on the same side as the alpha carbon. They're both carbons. There's not as big a steric difference between those two options. And so at equilibrium, you can observe both of these conformations for Proline. And so what Raines would do is he would change things about this molecule to see if he could strengthen the N to pi star interaction. and he would use the equilibrium constant between cis and trans as a measure for how strong that n to pi star interaction was, because of course there's one here but not one there. And you can actually do this by NMR, and it's quite simple. One of the features he discovered that influenced this equilibrium was this remote carbon, the delta carbon. He observed that substitution on the delta carbon could influence the equilibrium between cis and trans isomers, and by influencing the strength of the n to pi star interaction. I'll just point out, maybe, because this difference between cis and trans can be confusing, that in amino acids that are not proline, there is a side chain here and a hydrogen there. So there's a clear difference in sterics between cis and trans, right? Here, in the trans configuration here, the methyl or the carbon here is opposite to the alpha carbon there. It's cis to a proton, which is not very big. In contrast, if you made the cis amide, now your carbon here is on the same side as the alpha carbon there, and that's more sterically demanding. So in the case of regular amino acids, the trans configuration is preferred, but for proline, there's not as much a preference for cis versus trans. All right. All right, so that's one layer. For the discussion today, just think, okay, trans configuration is slightly more stable than cis because of this, what I've told you is an n to pi star interaction. We'll talk about that a little bit later. But how might the gamma carbon influence that equilibrium? Well, within proline, there's sort of two main ring conformations that you can draw. And this is what I was struggling to draw last time, and so I will try more. All right, here's the alpha carbon. Don't totally like that. Maybe we'll go even a little bit more exaggerated. Okay, so beta carbon, gamma carbon, delta carbon. Here's the carbonyl carbon. Here's the alpha carbon. Here's a proton. All right. All right, and then what will be important for our discussion is to fill in protons there so we can think about ring conformations. This is called having the gamma carbon at this point sort of above the 4 atoms here. I don't know, maybe we can run out of colors. So if you think of that being sort of a plane, and this is the envelope that's puckering up above the plane, we call this the C gamma endo pucker. And the alternative is the C gamma exopucker, which looks something like this. So here's your nitrogen, here's your alpha carbon. Oops, I want to make sure I do that right. Here's the beta carbon. Here's the delta carbon, and then in the endopucker, or sorry, the exopucker, the gamma carbon is down. Here's your carbonyl carbon, here's your amide nitrogen, here's a hydrogen, and then we'll fill in protons as needed. Okay, so do you see how in the drawing on the right, this is the C gamma exopucker. Don't worry about why we call one endo versus exo. Just know that they're different. But yeah, can you see how in the conformation on the left, that gamma carbon is above sort of the plane of those 4 other atoms, whereas in the conformation on the right, it's tipping down below. Okay? Right. So it turns out that in the C gamma endo pucker, there is, as you might expect, a little bit of steric repulsion between the CH on the gamma carbon and the carbonyl oxygen. And that steric repulsion makes it difficult for this carbonyl carbon to be in the right place for that N to pi star interaction that I was telling you about. It's actually much easier to have an N to pi star interaction over here for the C gamma exo pucker. You can have the interaction in both places, but the steric repulsion here weakens the N to pi star interaction. Okay.
Sorry, Dr.
Yeah.
Price, this might be like maybe taking us a bit backwards, but I think I'm confusing the whole thing. When we started, we said that actually the Cis and Trans, unlike in this other side, maybe because of the cyclopentyl ring.
Right.
The Cis and Trans are more like, it doesn't really matter, one is not preferred over the other.
So there is a small preference, but it's way less than it is for an amino acid that is not cyclic.
Okay, so that preference is because of the N to pi interaction?
That's right.
Okay.
Yeah, the equilibrium constant is actually close to 1, but Raines used this as a way to see what affects the strength of the N to pi star interaction. He made little changes in the structures of what was here, or the how electron poor the carbonyl was, and then he observed changes in that equilibrium constant. Since it was close to 1, any changes were easy to observe, and so you could easily measure changes in sort of half a kcal per mole or less. Yeah. All right. So what we're saying is that Raines found that the equilibrium between cis and trans amides was influenced by where this gamma carbon was, because where the gamma carbon was influenced the strength of the N to pi star interaction, and that in turn influences the cis-trans equilibrium. Kind of convoluted. I mean, you say that again. The gamma carbon, its position either up or down, influences the strength of the N to pi star interaction, and that influences the equilibrium between cis and trans amides. And it's this trans configuration that you want in, say, the protein collagen. So Raines and his group asked, is there something we can do to this gamma carbon that might influence whether we have an endo versus exo ring pucker? And the first place they looked was in just what nature does. As I told you, I think last time, nature uses the amino acid hydroxyproline, and that amino acid has the following stereochemical configuration. So here is the carbonyl carbon, alpha carbon, nitrogen, which is attached to something else, beta, gamma, delta, and on the delta carbon there is an OH group that is down. And collagen has a characteristic 3 amino acid sequence, which I forget. I think the third one is glycine. I think the first amino acid is proline, the second is hydroxyproline, and that repeats. So it's present a lot. in proline. I might have mixed these two places up, so don't worry if you find out at some point that they were switched. Just understand that hydroxyproline is favored a lot in collagen. So the Raines group asked, well, is it possible that having that OH group there on that delta carbon influences whether we adopt the endo versus exo pucker, and in turn influences the strength of the end to pi star interaction? So let's just modify our drawing for proline. Let's put the OH group, which is down here, versus here. And let's examine that conformation and see whether anything makes sense in terms of whether just looking at whether that OH group would influence the stability of the endo versus the exo pucker. So to do that, we're going to look down the bond between delta and gamma carbons. So put your magic, evil, bloodshot Sith Lord eyes in the page, and then look down that bond between delta carbon and gamma carbon. So we'll draw a Newman projection. The delta carbon is in the front, the gamma carbon is in the back. It looks like on that delta carbon in the front we have a hydrogen that is down. We have another hydrogen that's up, and then the nitrogen from proline is here. And of course that nitrogen's attached to two other things, which at this point we don't care about. Then in the back, on that gamma carbon, I would have a proton that's up, an OH group angled down, and then I guess the beta carbon here. Does that look reasonable? All right, so let's do the same thing, only this time we're still going to look down that bond between delta and gamma carbons, though we sort of have to place our eye a little bit over, and we'll just look down that bond between delta and gamma. Here is in front the delta carbon. It looks like on that carbon a hydrogen should be pointing up. It looks like a hydrogen should be angled to our left. Let's see, and then a nitrogen would be angled down towards our right. In the back on that gamma carbon that we can't see, the OH group would be pointing down, the hydrogen would be pointing this way, and then the beta carbon would be here. Does that look reasonable? Okay. So let's look, and based on what we learned about the gauche effect, let's see whether we can determine or predict which conformation should be more stable. Now remember, the gauche effect occurs, we learned, because in 1,2-difluoroethane we found that having the two fluoros gauche to each other was better because we could have the higher energy carbon hydrogen filled sigma bonding orbitals overlap with the lower energy carbon fluorine sigma stars. So which of these two do you think provides a more stable situation? Having OH anti to the nitrogen, or gauche? Sterics would tell you anti, but in reality electronics tell you gauche, and that actually overcomes the steric preference. So yes, having when oxygen and nitrogen are gauche to each other, this allows for, remember, carbon-oxygen bonds will be lower in energy than carbon-carbon or carbon-hydrogen bonds. So this allows, in the case of the oxygen, I'll just draw a filled carbon-hydrogen sigma bonding orbital in the front to overlap with the empty the empty carbon oxygen pi star in the back, which there would be a lobe behind the carbon oxygen bond pointing away from the space between the two nuclei. There would be a node here, a small lobe here, and a larger lobe there. So what I've drawn here is the carbon oxygen sigma star, and in the front you've got this filled carbon hydrogen sigma bonding orbital. So this allows for carbon hydrogen sigma bonding orbital to overlap with the carbon oxygen sigma star. It also allows for a carbon hydrogen bonding orbital to overlap with the carbon nitrogen sigma star. And that's better than over here, where you'd have a lower energy carbon oxygen sigma overlapping with the carbon nitrogen sigma star and vice versa. And all of this is because electronegative heteroatoms lower the energy of bonding and anti-bonding orbitals. It's like you move them down like that. All right, so that's an example of the Gauche effect. Anything you want to ask about that? So the Raines group went on to say, okay, let's build a better collagen. Could we make this preference even better? Well, what would be more electronegative than oxygen? You just look at the periodic table. Fluorine. Okay, so could we make the preference even better? And yes, if you replace that oxygen with a fluorine, that Gauche effect is even stronger because fluorine is more electronegative than oxygen. That creates an even stronger preference for the C-gamma exopucker, which strengthens the N to pi star interaction, makes the trans configuration stronger, and then that stabilizes collagen. Another thing they went on to do, so this is called a stereoelectronic effect because the stereochemistry at the gamma carbon and the electronegativity of the heteroatom at the gamma carbon influence the conformation of this molecule. So you'll hear people talk about stereoelectronic effects. That usually involves an orbital interaction in the molecule that's influenced by electronegativity and that can influence the conformation of the molecule. Okay, so what if instead you wanted to favor the endopucker? I'm going to just copy the endopucker because I want it to not be so small, but we're also going to draw something nearby. So what if okay, and we will just not worry about the steric repulsion here or what it does to the N to pi star interaction. We'll just say there's some reason why we want an endopucker. Maybe we found a protein where that happens and we want to make it even more, we want to make an amino acid that's even more biased for that situation. Can you think of something you could do to this molecule to favor the endopucker? Using the Gauche effect, let's say. And maybe look at this Newman projection. With the endopucker, the OH and the nitrogen are anti to each other. So could you change this molecule? Go ahead.
If you put the OH where the hydrogen is on the endo.
Okay, so let's just switch the stereochemistry, right? Let's go ahead and put the OH here, make the other version, the other diastereomer of hydroxyproline. Then if you look down and do the Newman projection, then with that change present, now the heteroatoms on the adjacent carbons are now gauche to each other. So Raines's group discovered, yeah, you have the OH group down, or the fluoro down there. You're going to favor the C-gamma exopucker, but if you have it up, you're going to favor the C-gamma endopucker. They also discovered something in terms of sterics that you could do, and this has to do with what I told you about steric clashing between these two groups. Suppose you wanted to make a supercharged hydroxyproline derivative that would really, really, really favor the C-gamma exopucker. Can you think of something you could do using the principle of steric repulsion, installing a group somewhere to make the exopucker even more favorable? Looking at something, some kind of repulsion that might be present over here that wouldn't be present there. Any guesses? Any thoughts? Take a risk. Nobody wants to roll the dice.
Have something electronegative.
Have something electronegative? Okay, where?
Where the H is.
Okay. So you want to put something there. Okay. Good. So if you wanted to use sterics, what would you do? Something bigger than hydrogen? Sure. So so you could choose, it turns out you don't, the Raines group chose methyl. It turns out you don't necessarily want another electronegative heteroatom there, because then you'd have a gauche situation no matter which conformation you were in. For example, if we switched that hydrogen to another OH group, then it doesn't matter which conformation you're in, you still have the heteroatoms gauche to each other. So to just prefer to strengthen the preference for this C-gamma exopucker, the Raines group put a methyl group there. So you've got in this conformation not only the absence of the gauche effect, but also steric repulsion between those two groups. And then when you get over to the C-gamma exopucker, you get the gauche effect and the methyl group's far away from that other group. It's sort of, you, in going from here to here, there's just this big sigh of as you relieve steric strain and you get the gauche interaction. Okay, so this is kind of a fun story. It turns out the Raines group started publishing on this in 1996. And their most recent publication on the subject, I think, was either last year or a couple of years ago. So they've gotten a huge amount of research mileage off of this effect. And it's kind of one of those things where you're like, you look at it, you're like, dang it, why didn't I think of that? And actually, that really characterizes Ron Raines's research. He has this way of seeing things in molecules that nobody else sees, but that after the fact we all think, well, I should have been able to see that. Just sort of kicking yourself that you didn't discover that. So that's an example of a stereoelectronic effect. There's more we could talk about in the chapter. I think the one thing I might want to make you aware of, because it will influence how you see carbohydrate chemistry, is one last example of a stereoelectronic effect, and it's called the Anomeric Effect. And if you're in the Savage Lab, you're going to see this and think about it a lot. What do we mean by anomeric effect? Well, let me draw a simple molecule. This is not a carbohydrate, but it's sort of similar to a carbohydrate because it's got this functional group here, which happens to be an acetal. An acetal is one carbon attached to two OR groups. And acetals can undergo what's called, cyclic acetals can undergo what's called mutarotation because they exist in equilibrium with an open chain form. So I'll just show you that having the OR group be equatorial versus axial, those two are in equilibrium. And if you look at that, you think, hold on, that's an interchange between stereoisomers. Yeah, it looks like you're doing Lego bond disconnect chemistry there, popping the proton off and putting it on someplace new. The reason you can do that is because these groups are both, these conformations are both in equilibrium with a high energy open chain form. Okay, and so all you need to do is have the chain open up, and then you can rotate around this carbon, swap the positions of the hydrogen in the OR group, and you can have that OR group equatorial versus axial. And if you were thinking just about sterics and you looked up A values, which of those two conformations would you think was more favorable? We think equatorial, right? Because you're avoiding those axial interactions. It turns out that it's not as favorable as you might think. So I wish I had a number for this particular molecule. I don't. The axial configuration is not necessarily more stable than the equatorial configuration, but it's more stable than you would think, based solely on steric considerations. A couple of terms that may help actually, or that you will hear when people talk about configuration at acetal carbons. I guess just for the sake of definition, people will call this the anomeric carbon. And they will call this, the one on the left, they will call that the beta, oh, Joshua, I get this wrong every time. They will call this the alpha anomer. And this one where the OR group is up, they will call that the beta anomer. Where anomer now is a term that's used to describe two isomers that differ in configuration at that anomeric carbon. In this case, they would be enantiomers of each other. If we had other stereocenters, they'd be diastereomers. Okay, so the question is, why might that be? And there's a couple of answers to that, and one of them has to be is related to dipoles. So there's a dipole in this direction associated with this carbon-oxygen bond, and then there's a dipole in this direction associated with these two carbon-oxygen bonds. Those dipoles oppose each other, and as to whether or not that's favorable, I think it sort of depends on the solvent. But dipole cancellation can be something that's good in nonpolar solvent. Nevertheless, I don't think that's the major consideration here. The major consideration really is an N to sigma star interaction between lone pair electrons on the ring oxygen and the carbon oxygen sigma star on the adjacent carbon. So what we'll do to visualize this, I'm not sure what the best way is. Yeah, let's just look down the bond between the oxygen in the back and the carbon in the front. We'll draw a Newman projection. You can't see that oxygen in the back. Here's the OR group that's down in the front. Here's the hydrogen, and here's the ring. And then in the back, you have an oxygen. Here's the ring. And then you have two different lone pairs. One of them is probably in a p-rich orbital, and the other is probably in an s-rich orbital for reasons we talked about back in chapter 1. So you have the p-rich lone pair here, and then the s-rich lone pair here. That p-rich lone pair is more reactive because it's higher in energy, and then the s-rich lone pair is less reactive because it's lower in energy. Now in the front, let's draw. So this is the lone pair on oxygen in the back. In the front, let's draw the sigma star. There would be a node in between the two nuclei, a small lobe here, a small lobe there, and a large lobe here, and another large lobe there. If we fill in the phases, we can see you've got overlap, considerable overlap down here and here between a filled orbital in the back and an empty sigma star orbital in the front. We call that sometimes, let's see, N for non-bonding lone pair, N to sigma star hyperconjugation. We're using, in this case, we're using a hybrid between valence bond theory and molecular orbital theory. We're thinking about bonds as being electrons localized between two atoms, but we're remembering the presence of antibonding orbitals, and then we're using hyperconjugation to allow us to delocalize electrons. It will get us to basically the same answer as molecular orbital theory will, but without having to do any math. So do you see how in the back the lone pair overlaps with the sigma star in the front? Any questions about that? In contrast, you should convince yourself later that the lone pair, the p-rich lone pair in the back, the one that's higher in energy and a better donor, is not going to overlap with the sigma star for the equatorial OR group. And so this is another example of a stereoelectronic effect, because stereochemistry determines whether or not this orbital interaction can happen. So just a few other examples of the anomeric effect, and some of these I actually do have numbers on. If you look at per acetylated glucose, that is glucose but with all the OH groups tied up in acetyl esters, and measure the equilibrium constant between having the groups equatorial versus having that group on the anomeric carbon be equatorial versus axial. Goodness, my chairs are ugly today. That's something that a chemist might say that an average person will not say. It's not like you wake up and go downstairs and say, goodness, my chairs are ugly today. The equilibrium constant here is, or the ratio of axial to equatorial configurations is 5:1. That's opposed to what Sterix would say, but it's consistent with the anomeric effect. As you might expect, depending on the strength of this carbon heteroatom bond, that bond that's on the anomeric carbon, you can make the anomeric effect stronger. Suppose you choose an atom that has a weaker bond with carbon. A weaker bond with carbon would mean that the sigma star is lower in energy. So let's look at the equilibrium constant. You know what? I don't like to draw chairs that direction. That's my problem. That feels much better. Somehow. Doesn't make any sense. The equilibrium constant between these two isomers. In this case, they're diastereomers. One has the Cl group down, the other has the Cl group up. Notice these are not different chairs. We're not flipping chairs. We're just changing the configuration at the anomeric carbon by going through the open chain form. You've got a preference 32 to 1 for the axial versus the equatorial configuration. That's a bigger preference than for the oxygen, and that's because the carbon-chlorine bond is weaker than the carbon-oxygen bond. And therefore, the carbon-chlorine sigma star is lower in energy. All right, so you're going to see that a lot. And remember that is a factor in whether the alpha versus beta anomers are more stable versus each other. There's a lot of different chemistry techniques for getting the alpha anomer versus the beta anomer. And if you go to the Savage Lab, you'll learn lots about that. Okay, so that sort of ends chapter 2. There's a ton of stuff we're leaving behind, but I think it's time to move on and talk about non-covalent interactions. Ton of stuff I used to think was important in chapter 3 that I no longer think is important, so we're going to skip it if that's okay. So what do we mean by non-covalent interactions? We mean any favorable interaction having two groups close to each other. That's Apple Pencil battery is low. Thank you. Having two groups close to each other where the free energy is lower if they're close to each other versus far apart. Only it's not a full covalent bond. So generally for non-covalent interactions, we're looking at them being worth anywhere from, 5 to 20 maybe kilocalories per mole. In contrast, covalent bonds in organic chemistry, depending on what kind of bond you've seen in your computational assignment, covalent bonds in organic chemistry tend to be worth, sort of 80 to 100 or more kilocalories per mole. So non-covalent interactions are worth a fraction of what a full-on covalent bond is worth. But don't let that deceive you. Remember that the definition worth, and when I say worth, I mean in terms of delta G for having the interaction versus not. These would be negative numbers, but anyway. Remember what we've said before in general chemistry, delta G equals minus RT ln K. Or alternatively, K equals the number E, or the exponential of minus delta G over RT. If you let delta G equal minus 1.36 kilocalories per mole, and if the temperature is 298 Kelvin, then K equals 10. Right? If K, I suppose it goes without saying that if delta G equals 0, K equals 1. So even a small difference in free energy between, say, having an interaction versus not having an interaction can end up making a huge difference in equilibrium constant. You can go from 1 to 1 to 1 to 10. And of course, you tack on each unit of each 1.4 kcals per mole is worth a factor of 10 in equilibrium constant. So if an interaction were worth, say, 5 kilocalories per mole, now you're looking at an equilibrium constant of like 10,000 or something like that. It can dramatically bias equilibria in biological processes. And so these interactions are important for understanding how the organic chemistry of biology. So we're going to talk about them, and basically they're anything you can think of where a full charge or a partial charge or even a temporary partial charge might interact with another full charge, partial charge, or temporary charge. So your first classic example is the ion pair. And in an ion pair, a cation and an anion are close enough that the attraction between them, according to Coulomb's law, is larger than the thermal energy that's available to separate them. And in thinking about thermal energy, I want you to always think of temperature as average kinetic energy of molecules in a system, because that's exactly what it means. Molecules are moving faster, they have higher temperature. We tend to think of temperature, oh, something's hot, oh, something's cold. No, it's that the molecules are moving slower in cold things versus faster in hot things. So, delicious ice cold water. No, the water molecules are moving slower in here than they might be from the tap water, right? Okay, so what is the relationship? For these non-covalent interactions, it's good to understand the relationship between charge and partial charge and the distance between two ions. So the energy of having ions close together you just get from Coulomb's law. Q1 is charge 1, Q2 is charge 2. Then we got a bunch of constants in the denominator, 4 pi, and I formulated this a little bit differently. E naught is the permittivity of a vacuum, and then this number E, or epsilon naught, epsilon here is something called the dielectric constant, and it's related to how much more or less permittivity does a particular medium have relative to a vacuum. This number is important because, as you can see, if the dielectric constant is large, the energy of the interaction between two charges goes away, right? Or starts to be attenuated. The dielectric constant, let's see, in my notes it says it's a measure of how responsible the medium is to an electric field, and therefore its ability to screen charges from each other by opposing the applied electric field. So if you have two charges in water, if the water molecules between them can orient themselves aligning with that field, they will actually prevent the charges from seeing each other to the same extent. So this tells you that when we think about ion pairs, context is going to be important. You might expect two charges in a vacuum to have a much stronger interaction than two charges in water. Incidentally, as you teach your first semester organic chemistry students about interactions, they're going to come from Gen Chem with this idea that ionic bonds are really strong, right? Well, it's always relative to what, right? So relative to being infinitely apart in a vacuum, sure, they're very strong. But then how come they come apart in water? Right? And the reason is that it has to do with this dielectric constant, and it also has to do with the ability of water to solvate the charges once they're dissociated from each other. So we'll talk more about that next time. That's enough to be going on with. I will see you on Wednesday.